Every point of light belongs to a structure so vast that even the idea of counting similar structures elsewhere begins to strain intuition. From inside one galaxy, the universe feels sparse, empty even. Large distances dominate perception, not numbers. But as telescopes improved and surveys deepened, that sense of emptiness began to dissolve. Faint smudges multiplied. Deep images revealed thousands of galaxies where none had been visible before, and slowly a quiet problem emerged. How many galaxies are actually out there? Not how many stars, not how big the universe is in theory. But how many separate, gravitationally bound systems of stars exist within the part of the universe that can, in principle, be observed? A question that sounds simple, almost innocent, yet refuses to settle on a single number. Every attempt to answer it runs into limits of light, limits of distance, limits of definition. The further outward observations reach, the more galaxies appear, often smaller, fainter, and easier to miss. And beyond a certain point, even existence itself becomes something that must be inferred rather than seen. This video is not about rushing toward a final figure. It's about how astronomers approach the problem at all, how nearby galaxies inform distant ones, how surveys, deep fields, and simulations slowly build a picture that is always provisional, and why the universe seems content to reveal structure without ever offering completion. Welcome to the Sleepy Scientist. If this kind of slow, thoughtful exploration helps you unwind, consider liking the video and subscribing to the channel. And while you're settling in, let me know where you're watching or listening from. From inside a city under a dark sky, or somewhere in between. There's only one galaxy that can be experienced from the inside. Every other galaxy appears as a distant object, a patch of light against darkness, but this one surrounds the observer completely. Stars appear in every direction. Dust lanes stretch across the sky. A faint band of light arcs overhead on clear nights, marking the dense disk of the Milky Way seen from within. This embedded position feels intimate, even familiar, yet it quietly distorts perception in ways that are easy to overlook. From the inside, symmetry is difficult to judge, scale is hard to measure, completeness is almost impossible to assess. There is no external vantage point from which the full structure can be seen at once. Instead, the Milky Way must be reconstructed indirectly, star by star, region by region, using distance estimates, motion, and brightness as imperfect guides. That challenge shaped the earliest attempts to understand what kind of galaxy this actually is. At the beginning of the 20th century, astronomers attempted to map the Milky Way by counting stars in different directions. One of the most influential efforts came from Jacobus Kapteyn, who assembled one of the first systematic models of the galaxy using star counts and assumed brightness distributions. His model suggested a modest flattened system with the Sun located near its centre. It was elegant, mathematical, and deeply wrong. The error was not carelessness, it was invisibility. Interstellar dust absorbs and scatters light, especially in the plane of the galaxy where stars are most densely packed. Distant stars appeared dimmer not because they were few, but because their light was being quietly erased along the way. Kapteyn had no way to account for this properly. As a result, the Milky Way appeared smaller, neater, and more complete than it actually is. This early mistake matters because it reveals a deeper pattern. When observation depends on light alone, absence can masquerade as emptiness. What is not seen may still exist in large numbers. That lesson echoes through every later attempt to count galaxies beyond the Milky Way. As techniques improved, astronomers began to look not only at where stars were, but how they moved. Stellar motions offered a different kind of information, one less dependent on brightness alone. By tracking how fast stars orbited the galactic centre at different distances, it became possible to infer how much mass the galaxy contained, and how that mass was distributed. This is where rotation curves enter the story. When orbital speed is plotted against distance from the centre of a galaxy, classical physics predicts a steady decline beyond the region containing most of the visible matter. Instead, observations showed something unexpected. Stars far from the centre were moving just as fast as those closer in. The galaxy behaved as though it contained far more mass than could be seen. Vera Rubin's careful measurements of galaxy rotation curves made this discrepancy impossible to ignore. The implication was not a minor correction, but a structural revision. A galaxy was no longer just the sum of its visible stars and gas. It was embedded in a vast halo of unseen mass, now known as dark matter, extending far beyond the luminous disk. This changed what it meant for something to qualify as a galaxy. A galaxy was not defined solely by light. It was defined by gravitational coherence, by the presence of a massive structure capable of binding stars together over billions of years. Suddenly, the visible portion became only a tracer, not the whole. From inside the Milky Way, this realization complicates everything. The bright spiral arms that dominate the night sky represent only a fraction of the system's true size and mass. Surrounding them is a dark matter halo stretching several times farther than the visible disk. Embedded within that halo are globular clusters, streams of stars from long-past mergers, and satellite galaxies so faint they barely register against the background. If the full extent of the Milky Way cannot be seen directly from within, then any attempt to use it as a template for other galaxies must proceed cautiously. What appears complete may be partial. What appears typical may be biased by perspective. Internal uncertainty accumulates quietly. Distances to stars carry error margins. Dust distribution varies irregularly. Stellar populations overlap in projection. Even basic quantities such as total stellar mass and diameter are revised as new data arrives. Each uncertainty is manageable on its own, but together they remind the listener that the Milky Way is not a known object in the everyday sense. It is a model, refined continuously, never finished. This matters deeply when the goal is to extrapolate outward. Counting galaxies elsewhere relies on assumptions about what galaxies generally look like, how massive they tend to be, and how their light relates to their total mass. If the home reference point is itself only partially understood, then every larger estimate inherits that uncertainty. There is also a subtler issue. Living inside a large spiral galaxy normalizes largeness. Spiral arms feel common because they dominate nearby views. Dense star fields feel typical because they fill the sky. Yet when the local universe is examined more broadly, massive spirals turn out to be relatively rare. Smaller galaxies, faint galaxies, and irregular systems dominate by number, even though they are easy to overlook. The Milky Way is not misleading because it is unusual, but because it is prominent. Its brightness and size command attention in a way that smaller systems do not. From the inside, that prominence can feel like a baseline, when it is actually an outlier in some respects. So the very first step in asking how many galaxies exist is not outward, but inward. It begins with recognizing that even the nearest, most familiar galaxy is only partially visible, partially understood, and deeply shaped by perspective. The problem of counting galaxies does not begin at the edge of the observable universe. It begins here, inside a system that hides a significant fraction of itself from its own inhabitants. Once that is accepted, the wider problem becomes easier to frame, even if it does not become easier to solve. When attention moves just beyond the Milky Way, the first galaxies that come into view are not subtle. The Andromeda Galaxy dominates the nearby sky in scale and presence, stretching across a region several times the width of the full moon when observed under dark conditions. It is massive, bright and structured, with sweeping spiral arms and a dense central bulge. Slightly farther away sits the Triangulum Galaxy, smaller but still clearly defined, another spiral system with visible organization and ongoing star formation. Together, these neighbors feel familiar. They look like galaxies are supposed to look. Large, orderly, bright enough to announce themselves even at great distances, and for a long time that familiarity shaped intuition in a quiet but powerful way. When the nearest examples resemble one another, it is tempting to assume they are typical. The Milky Way, Andromeda, and Triangulum all belong to the same broad class of spiral galaxies. They contain hundreds of billions of stars, rotating disks and extended halos of gas and dark matter. Studying them side by side creates the impression that galaxies, in general, are large, luminous, and easily recognizable. That impression turns out to be misleading. Before that became clear, however, astronomers had to answer a more basic question. How far away are these neighbouring systems really? The difference between a galaxy being a few 100,000 light-years away or several million light-years away completely changes how its size and brightness are interpreted. This is where refinements to the distance ladder reshaped understanding. The distance ladder is a collection of overlapping methods used to estimate cosmic distances, each calibrated against the next. Cepheid variable stars play a central role at nearby scales, because their intrinsic brightness is linked to their pulsation period. Once that relationship was established, cepheids became reliable beacons for measuring distances to nearby galaxies. Alan Sandage devoted much of his career to refining these measurements, improving calibrations, reducing systematic errors, and clarifying which distance indicators could be trusted at different ranges. His work helped stabilize estimates of how far away Andromeda and Triangulum actually are, placing them firmly outside the Milky Way and anchoring the scale of the local universe. With distances better constrained, comparisons became more meaningful. Andromeda emerged as slightly larger and more massive than the Milky Way, while Triangulum appeared smaller and less evolved, yet still clearly a spiral galaxy. These differences were interesting, but they did not immediately challenge the underlying assumption that spiral galaxies represented the standard model. That assumption was reinforced by visibility. Large spirals are bright, their stars are numerous, their gas clouds glow, their shapes stand out clearly against the darkness of space. When telescopes sweep the nearby universe, these systems demand attention simply because they are easy to see. Visibility, however, is not the same as abundance. This distinction is subtle at first. When catalogues of nearby galaxies were assembled, the most prominent objects naturally filled the pages. Spirals with clear structure dominated early lists, not because they were most common, but because they were easiest to identify at distance. Smaller, fainter systems blended into the background, often dismissed as noise or ignored entirely. The result was a skewed picture of the galactic population. If attention is drawn primarily to luminous spirals, then spirals begin to feel typical. If spirals feel typical, then estimates of how many galaxies exist begin to scale from that expectation. Bright galaxies become the reference point and everything else becomes an afterthought. This bias is not a failure of reasoning. It is a consequence of how light behaves. Bright objects announce themselves across space. Dim objects do not. A small galaxy containing a few million stars can be overwhelmed by foreground stars, dust, or background glow. At even modest distances, such a system may vanish entirely from view. In contrast, Andromeda would remain visible even if it were several times farther away. Its sheer size and brightness granted a kind of observational privilege. That privilege distorts intuition. When galaxy populations are examined statistically, a different picture emerges. Massive spirals like the Milky Way and Andromeda are impressive, but they are not numerous. They occupy a small fraction of the total galaxy count. Most galaxies are far smaller, far dimmer, and far easier to miss. This is where Triangulum quietly becomes more informative than it first appears. Though still a spiral, it is significantly less massive than its two larger neighbours. Its lower stellar mass and simpler structure hint at a broader population of modest galaxies that do not dominate their surroundings. Even Triangulum, however, remains relatively bright compared to the faintest systems nearby. The similarity among the nearest large galaxies once encouraged the idea of galactic uniformity. It suggested that galaxies formed in broadly similar ways, grew to comparable sizes, and followed predictable evolutionary paths. That view simplified early models and made the universe feel more orderly. As surveys expanded and sensitivity improved, that simplicity began to unravel. The local universe revealed a menagerie of systems that did not resemble spirals at all. Irregular galaxies with chaotic shapes, elliptical galaxies lacking disks entirely, dwarf galaxies barely holding themselves together gravitationally. Many of these systems were found not in isolation, but clustered around larger galaxies like satellites, their existence overshadowed by the brilliance of their hosts. This realization forces a recalibration of intuition. The galaxies that dominate attention are not the ones that dominate numerically. They are statistical outliers in terms of mass and brightness, even though they feel central to experience. The nearest neighbours, then, play a dual role. They provide essential calibration points for distance, structure, and dynamics. At the same time, they quietly mislead by overrepresenting a particular class of galaxy. Without careful correction, they encourage overconfidence in patterns that do not generalize. Recognizing this is an important step. It marks the moment when the problem of counting galaxies shifts from identifying prominent objects to accounting for populations that do not announce themselves. The universe does not hide most of its galaxies deliberately. It simply makes them easy to overlook. Once that is understood, attention naturally begins to drift away from the brightest neighbours and toward the smaller, quieter systems that surround them. Those systems, though less impressive individually, hold the key to understanding how many galaxies truly exist. Galaxies rarely exist alone. Although it is tempting to imagine them scattered independently through space, most galaxies are born, evolve, and persist within shared gravitational environments. These environments shape how galaxies form stars, how they grow, how they lose material, and how long they survive as distinct systems. To understand how many galaxies exist, it is not enough to count individual objects. It becomes necessary to understand the systems they belong to. This is where the local group becomes more than a convenient label. It is not simply a list of nearby galaxies. It is a gravitationally bound, evolving system spanning several million light-years, held together by the combined mass of its largest members and their extended dark matter halos. The Milky Way and Andromeda dominate this system, with Triangulum contributing additional mass, while dozens of smaller galaxies orbit, drift, and interact within the same shared gravitational landscape. Thinking in terms of a group immediately changes the nature of counting. Galaxies inside a group do not behave as isolated objects. Their histories overlap, their futures are intertwined, their present appearances often reflect past encounters rather than intrinsic properties. This perspective has been explored in depth by researchers such as Yuri Efremov, whose work emphasized the importance of environment in shaping stellar populations and star formation histories. Rather than treating galaxies as closed systems, this approach treats them as participants in a dynamic network of gravitational influence. In doing so, it reframes how galaxy population should be interpreted. Within the local group, interactions are not rare events. They are a defining feature. Satellite galaxies pass repeatedly through the outer regions of larger hosts. Tidal forces stretch them, compress them, and sometimes tear them apart. Gas can be stripped away, shutting down future star formation. Stars can be pulled into elongated streams that wrap around larger galaxies, leaving visible scars of past encounters. These processes directly affect visibility. A dwarf galaxy that once contained active star formation may fade after losing its gas, becoming harder to detect against the background. Another may be stretched so thin that it no longer resembles a galaxy at all, blending into stellar debris. From a purely observational standpoint, such systems are easy to miss or misclassify. This matters because dwarf galaxies dominate galaxy populations by number. In the local group alone, more than 50 small galaxies are known, and new ones continue to be discovered as surveys improve. Many of these systems contain only a few million stars, compared to the hundreds of billions found in the Milky Way. Individually, they are unimpressive. Collectively, they define the population. The local group demonstrates something fundamental. The smallest meaningful unit for galaxy statistics is not the individual galaxy, but the group environment. Counting galaxies without accounting for their interactions risks double counting some systems and missing others entirely. For example, when a dwarf galaxy is disrupted and its stars become part of a stellar stream, should it still be counted as a galaxy? At what point does it cease to exist as a separate object? These questions are not philosophical curiosities. They directly influence population estimates. If only intact, star-forming galaxies are counted, then many systems are excluded. If remnants and transitional objects are included, the number rises. The group context determines which interpretation makes sense. There is also the problem of survival time. Galaxies within groups have finite lifetimes as independent systems. Over billions of years, smaller galaxies tend to merge with larger ones, or dissolve under tidal forces. The local group is not static. It is slowly evolving toward fewer, larger galaxies through mergers and accretion. This means that the number of galaxies present at any given moment is not representative of how many galaxies have existed over time. Groups reduce galaxy counts as they age. A snapshot taken today captures only the survivors. From a statistical standpoint, this introduces a strong bias. Older groups will contain fewer galaxies than younger ones, even if they began with similar populations. Counting galaxies without considering group age and interaction history leads to misleading comparisons across cosmic environments. Isolated galaxy counts suffer from another problem. Truly isolated galaxies are rare. Most systems that appear isolated are simply distant from obvious neighbours, or located in low-density regions. Even these galaxies are often embedded in faint filaments of dark matter and gas, subtly influencing their evolution. By contrast, the local group offers a relatively complete laboratory. Distances are well measured. Individual stars can be resolved in many member galaxies. Tidal features can be observed directly. This makes it possible to trace interactions with unusual clarity. Yet even here, completeness is elusive. Some dwarf galaxies remain hidden behind dust in the plane of the Milky Way. Others are so diffuse that they blend into the background. The known population is almost certainly incomplete. This reinforces a crucial point. If the nearest and best-studied galaxy group cannot be fully catalogued with confidence, then more distant groups are guaranteed to be incomplete. Their faintest members slip below detection thresholds. Their disrupted remnants are impossible to recognize. Counting galaxies as isolated points ignores these realities. It treats galaxies as static, independent units, when in fact they are transient structures shaped by collective dynamics. The local group shows that galaxy populations are not merely about formation. They are about survival. They depend on mass, environment, timing, and chance encounters. A galaxy's visibility today reflects not only what it is, but what it has endured. This is why galaxy groups are the smallest meaningful units for population statistics. They capture the context that determines which galaxies remain visible and which quietly vanish. Without that context, any count becomes an illusion of precision. Once this is understood, the task of counting galaxies expands again. It is no longer about tallying dots of light. It becomes an effort to account for systems in motion, shaped by shared gravity, evolving together over immense spans of time. And that makes isolated galaxy counts not just incomplete, but fundamentally misleading. If galaxies were counted by size or brightness alone, dwarf galaxies would barely register. They are small, faint, and often irregular in shape. Many contain only a few million stars, sometimes fewer, compared to the hundreds of billions found in large spirals like the Milky Way. From a distance, They fade quickly into the background, easily lost among foreground stars, dust and noise. Yet despite their modest appearance, dwarf galaxies dominate the universe by number. In any reasonably complete survey, dwarfs outnumber large galaxies by a wide margin. They are not rare exceptions. They are the default outcome of galaxy formation. Large spirals and ellipticals draw attention because they are dramatic and luminous, but dwarfs are the quiet majority, forming wherever small concentrations of gas collapse inside dark matter halos. For a long time, this dominance was easy to underestimate. Early galaxy catalogues were built around what telescopes could see clearly, and what they could see clearly were bright extended systems. Dwarf galaxies slipped through the gaps, not because they were uncommon, but because they were observationally fragile. That fragility became impossible to ignore in the early 2000s, when new wide-field digital surveys began to probe the sky with unprecedented sensitivity. As these surveys expanded, something unexpected happened. The number of known nearby dwarf galaxies began to climb steadily, not because the universe had changed, but because the threshold for detection had shifted. Beth Willman played a key role in this transformation through the discovery and characterization of ultra-faint dwarf galaxies orbiting the Milky Way. These systems are among the dimmest galaxies known, containing as few as a few thousand stars spread over regions hundreds of light-years across. Their total luminosity can be less than that of a single bright star cluster, yet their internal motions reveal that they are embedded in dark matter halos massive enough to qualify as galaxies. The existence of these ultra-faint dwarfs exposed a crucial limitation in early accounts. Galaxies had been missing not because they were hidden far away, but because they were barely luminous at all. Once survey sensitivity improved, these systems began to appear in large numbers, often clustered around larger galaxies. This discovery highlighted an uncomfortable truth. The number of galaxies one finds depends strongly on how faint one is able to look. Lower the detection threshold, and the count rises. Raise it, and the universe appears simpler and emptier than it really is. Dwarf galaxies are not just faint, they are also vulnerable. Their low masses make them susceptible to tidal stripping when they orbit larger galaxies. As they pass through the gravitational field of a massive host, stars can be pulled away, gas can be removed, and the remaining system can be stretched into elongated shapes. Over time, some dwarfs lose so much material that they are reduced to stellar streams, no longer recognizable as self-contained galaxies. This introduces the idea of a survival threshold. Below a certain mass, a galaxy cannot retain its stars and gas against external forces. It may form, but it will not persist for long. Above that threshold, it can survive repeated interactions and remain visible for billions of years. The exact value of this threshold depends on environment. A dwarf galaxy in isolation may survive with far less mass than one orbiting close to a giant spiral. This means that the same type of galaxy can have very different lifetimes depending on where it lives. From a counting perspective, this matters enormously. Some dwarf galaxies exist only briefly as identifiable systems, others persist quietly for cosmic timescales. A snapshot taken at any given moment captures only those that have survived up to that point. There's also the problem of classification. Many dwarf galaxies blur the line between galaxies and star clusters. Both can contain similar numbers of stars. Both can appear compact or diffuse. The key difference lies in gravitational binding and dark matter content, neither of which is directly visible. In practice, astronomers rely on stellar motions to make this distinction. If stars move too fast to be held together by their visible mass alone, the presence of dark matter is inferred, and the object is classified as a galaxy. If not, it is usually labelled a star cluster. This sounds straightforward, but in reality it is messy. Measurements are uncertain, sample sizes are small, boundaries are fuzzy. As a result, some objects sit uncomfortably between categories, included in some galaxy counts and excluded from others. Each of these decisions nudges the total number up or down. Dwarf galaxies also challenge intuitive ideas about shape and structure. Many lack clear disks or bulges. Some appear irregular, with star formation occurring in scattered regions rather than organized patterns. Others are spheroidal, containing old stars and little gas, their active phases long over. These differences are not cosmetic. They reflect distinct evolutionary paths shaped by environment, mass, and timing. When counting galaxies, treating all dwarfs as a single category can obscure this diversity, while splitting them too finely can inflate uncertainty. What remains consistent is their sheer abundance. In galaxy groups like the local group, dwarfs outnumber large galaxies by at least an order of magnitude. In richer environments such as galaxy clusters, the imbalance is even more extreme. This has a direct and unavoidable consequence for estimates of how many galaxies exist in the universe. If most galaxies are small and faint, then most galaxies are difficult to detect. Any survey that misses faint objects will systematically undercount the total population. As detection limits improve, counts rise. As classification criteria broaden, counts rise again. This is not a sign of error or indecision. It is a reflection of the underlying population. The universe does not consist of a modest number of grand structures surrounded by empty space. It consists of vast numbers of modest systems, many hovering near the edge of detectability, many shaped or damaged by their surroundings, many short-lived on cosmic timescales. Dwarf galaxies are the statistical backbone of galaxy counts. They set the scale, they dominate the numbers, and they quietly ensure that any attempt to count galaxies must remain provisional. When astronomers revise estimates upward, dwarfs are almost always the reason. Not because new physics has been discovered, but because the universe turns out to be more crowded at small scales than intuition suggests. Understanding this shifts the question of how many galaxies exist away from dramatic extremes and towards subtle limits. It becomes less about how far telescopes can see, and more about how faint a system can be and still be recognized as a galaxy at all. That recognition, fragile and conditional, is what keeps the total number rising. At first glance, the word galaxy feels unambiguous. A galaxy sounds like a clearly defined thing, a large system of stars held together by gravity, distinct from its surroundings and recognizable when seen. In practice, however, that clarity dissolves very quickly. Astronomers do not count galaxies the way one might count planets or moons. Before anything can be counted, it must be defined, and that definition turns out to be far more slippery than intuition suggests. One way to define a galaxy is through its dynamics. A galaxy must be a gravitationally bound system, meaning its stars move in ways that indicate they are held together by a shared mass. This criterion immediately excludes many loose associations of stars that appear clustered but are not truly bound. It also elevates the importance of stellar motions, because motion reveals mass, including mass that cannot be seen. Another approach focuses on stellar populations. A galaxy typically contains multiple generations of stars, often spanning billions of years in age. This suggests a long-lived system capable of forming stars repeatedly over cosmic time. By contrast, many star clusters form stars in a single burst, and then fade. That difference sounds straightforward, but in small systems the distinction can blur. Dark matter content adds yet another layer. Modern definitions often require a galaxy to be embedded in a dark matter halo. This criterion is especially important for dwarf galaxies, where the visible stars account for only a small fraction of the total mass. If stars are moving too quickly to be explained by their own gravity alone, dark matter is inferred, and the system is classified as a galaxy. Each of these definitions captures something real, but none is complete on its own. Some systems satisfy all criteria, others satisfy only one or two. The question then becomes which properties matter most. These ambiguities were explored in depth by astronomers such as Sidney van den Berg, who spent decades analysing galaxy morphology and classification. His work highlighted how easily galaxies resist tidy categorization. Even among large systems, shapes vary smoothly rather than falling into discrete boxes. Among smaller systems, the boundaries become even more porous. Vandenberg showed that classification schemes are not neutral descriptions. They encode assumptions about formation, evolution, and importance. When those assumptions change, the categories change with them. This has a quiet but powerful effect on galaxy counts. When astronomers publish estimates of how many galaxies exist, those numbers often differ not because the observations disagree, but because the definitions do. One study may include ultra-faint dwarfs as galaxies. Another may exclude them as star clusters. A third may classify the same object differently based on new data about stellar motions. Each choice is defensible. Each choice alters the final count. These shifts rarely make headlines. They occur in footnotes, tables, and methodological sections. Yet collectively, they move the number of known galaxies up or down by significant margins. The problem becomes even clearer when considering how galaxies support themselves against gravity. Some galaxies are rotation-supported. Their stars orbit a central axis in an organized disk, like the Milky Way or Andromeda. Rotation provides stability, and the system's structure is relatively easy to interpret. Others are pressure-supported. In these systems, stars move in many directions, held together not by coherent rotation, but by the collective effect of random motions. Elliptical galaxies and many dwarf spheroidals fall into this category. Their shapes are smoother, their dynamics less intuitive, and their boundaries harder to define. Pressure-supported systems challenge simple ideas of what a galaxy looks like. They may lack clear edges. Their stars fade gradually into surrounding space. In some cases, it is unclear where the galaxy ends and the background begins. This matters for counting. A rotation-supported disk presents a clear signal. A pressure-supported cloud of stars does not. Detection becomes sensitive to how far out one draws the boundary, which stars are included, and which are dismissed as foreground or background contamination. The issue grows sharper at small scales. Some ultra-faint systems contain only a few thousand stars. Their internal motions suggest dark matter, but the measurements are noisy. Their stellar populations resemble those of large star clusters. Their shapes are irregular. Classifying them requires judgment as much as measurement. Different research groups sometimes reach different conclusions about the same object. One catalogue lists it as a galaxy, another lists it as a cluster. Neither is obviously wrong. They're applying different thresholds. This is why taxonomy becomes a limiting factor in galaxy counting. The universe does not present galaxies as neatly labelled entities. It presents a continuum of structures, ranging from massive luminous spirals to barely bound stellar assemblages hovering on the edge of coherence. Counting requires drawing lines across that continuum. Those lines are not arbitrary, but they are not uniquely determined either. They reflect the current state of theory, the available data, and the questions being asked. A study focused on dark matter distribution may adopt one definition. A study focused on star formation history may adopt another. As a result, the number of galaxies is not a single objective fact waiting to be discovered. It is a quantity that emerges from a set of choices, each grounded in physical reasoning but none immune to revision. This does not mean galaxy counts are meaningless. It means they are conditional. They describe how many galaxies exist according to specific criteria, within specific observational limits, at a particular moment in scientific understanding. There's a quiet irony here. As telescopes improve and data becomes richer, the problem does not simplify. It becomes more detailed. More objects appear near the boundary. More exceptions demand explanation. More systems resist clean classification. In a sense, the universe becomes more crowded and less tidy at the same time. This is why published galaxy counts tend to be ranges rather than precise totals. They acknowledge that definitions matter. They admit that some objects sit uncomfortably between categories. They reflect humility rather than uncertainty. When astronomers say there may be hundreds of billions or even trillions of galaxies, that statement carries an implicit clause. It depends on what is counted, how faint is too faint, and where the line between galaxy and non-galaxy is drawn. Understanding this reframes the question itself. Asking how many galaxies exist is not just a question about abundance. It is a question about identity. It asks what kind of structures are considered meaningful, persistent, and worthy of a name. The answer evolves because the universe is more inventive than classification schemes. And every time those schemes are refined, the count shifts quietly in response. There was a time when galaxies did not exist as a category at all. The night sky contained stars, planets, and a scattered collection of faint misty objects known collectively as nebulae. Some were clearly associated with star formation inside the Milky Way. Others were unresolved smudges whose nature was unclear. Through the telescopes of the 19th century, they all looked broadly similar. Soft edges, no obvious stars, no reliable sense of distance. Without distance, size is meaningless. Without size, classification collapses. Astronomers could describe where these nebulae appeared in the sky, how bright they seemed, and sometimes how their light was distributed, but they could not say what they actually were. A faint spiral shape might indicate a nearby cloud of gas or an unimaginably distant stellar system. Both interpretations fit the data equally well. This ambiguity was not a failure of imagination. It was a limitation of tools. Telescopes of the time gathered relatively little light. Long exposures were difficult. Detectors were crude. Even large instruments struggled to resolve individual stars beyond the immediate surroundings of the Milky Way. As a result, many nebulae remained unresolved, their true nature hidden behind the same haze that made them intriguing. The problem was compounded by scale. If spiral nebulae were part of the Milky Way, then the galaxy itself would have to be enormous, extending far beyond the distribution of visible stars. If they were external systems, then the universe would suddenly become vastly larger than previously imagined. Both possibilities were unsettling, and neither could be tested decisively with the instruments available. Into this uncertainty stepped a different kind of observation. Rather than asking how nebulae looked, Vesto Slipher began asking how they moved. At the Lowell Observatory in the early 1900s, he turned a spectrograph towards spiral nebulae and measured their spectral lines with extraordinary care. What he found was unexpected. Many of these nebulae exhibited large Doppler shifts. Their spectral lines were displaced in ways that indicated motion at hundreds of kilometers per second, far faster than the typical motions of stars within the Milky Way. Some appeared to be approaching rapidly. Most appeared to be moving away. At the time, there was no accepted framework to interpret this. Cosmic expansion had not yet been proposed. The idea that the universe itself might be growing larger was not part of mainstream astronomy. Slipher's measurements stood alone, precise but puzzling. If spiral nebulae were small objects within the Milky Way, such extreme velocities would be difficult to explain. Stars orbiting the galactic center move at a few hundred kilometers per second at most, and those motions follow predictable patterns. The nebulae did not fit comfortably into that picture. Slipher did not claim to have discovered galaxies. What he provided was something more subtle and more important. He provided evidence that these objects were dynamically distinct from the stars around them. They behaved as though they were separate systems, not local clouds. Even so, interpretation lagged behind observation. Many astronomers continued to classify spiral nebulae as internal features of the Milky Way. Others argued they were external systems. The debate persisted not because one side ignored the data, but because the data were incomplete. Velocities alone could not establish distance. Without distance, size and nature remained ambiguous. This misclassification had a significant consequence. If spiral nebulae were assumed to be internal, then they were not counted as separate galaxies. They were treated as substructures within a single, large system. Population studies stalled because there was, by definition, only one galaxy to study. This bottleneck delayed the emergence of galaxy statistics by decades. Instrument limits played a decisive role. Early photographic plates were insensitive to faint stars. Even if a spiral nebula contained billions of stars, those stars would blur together into a smooth glow unless they were individually resolved. Only the nearest systems could be broken apart into discrete points of light, and even then only under ideal conditions. Dust further complicated matters. Dark lanes within the Milky Way obscured large portions of the sky, particularly along the galactic plane where many nebulae were observed. A distant galaxy viewed through dense dust could appear small and faint, easily mistaken for a local object. The universe was not only large, it was cluttered with obstructions. As telescopes improved incrementally, the picture shifted slowly rather than dramatically. Larger mirrors collected more light. Better optics improved resolution. Longer exposures revealed structure within some nebulae. Spiral arms became clearer. Bright knots appeared, suggestive of star-forming regions. Yet even these improvements did not settle the question. Structure alone could not distinguish between a nearby cloud and a distant galaxy. Nature, inconveniently, can produce similar patterns at very different scales. The turning point required a new kind of measurement, something that tied brightness to intrinsic properties rather than appearance, something that could break the distance deadlock. That solution would come from variable stars, whose predictable behavior allowed astronomers to measure distances far beyond the reach of parallax. But before that breakthrough arrived, the universe existed in a kind of conceptual limbo. Galaxies were there, but unnamed. Countless stellar systems existed beyond the Milky Way, but they were hidden inside a category that blurred the near and the far together. The universe was already crowded, but it looked sparse. This period of ambiguity shaped how astronomers thought about the cosmos. It encouraged caution. It reinforced the idea that classification must wait for measurement. It also left a legacy of humility that still matters. The lesson is straightforward but easy to forget. Observations do not speak for themselves. They are filtered through instruments, assumptions, and available frameworks. When tools are limited, interpretation narrows accordingly. The recognition of galaxies as separate worlds did not happen because the universe changed. It happened because the means to distinguish distance, motion, and structure finally converged. Once that convergence occurred, the population of the universe expanded almost overnight, not in reality but in understanding. Before that moment, galaxies were not rare. They were simply invisible as galaxies. And that invisibility reminds us that any count of cosmic structures is inseparable from the tools used to reveal them. For years, the argument over spiral nebulae was not about imagination or belief. It was about method. The disagreement that later became known as the Great Debate was, at its core, a clash between different ways of reasoning from incomplete data. One side argued from the distribution of stars and globular clusters within the Milky Way, concluding that the galaxy was vast enough to contain all known nebulae. The other side focused on the appearance and motions of spiral nebulae, suggesting that they were separate systems far beyond the Milky Way's boundaries. Both positions were grounded in evidence. Both relied on assumptions that seemed reasonable at the time. What neither side possessed was a reliable way to measure distances on truly extragalactic scales. Without distance, everything else remained uncertain. A spiral nebula could be small and nearby, or enormous and distant. Its brightness alone could not resolve the ambiguity. Structure did not help either, since nature has a habit of repeating patterns at different scales. The debate persisted not because the data were ignored, but because they were insufficient. The breakthrough came from a source that initially had nothing to do with galaxies at all. Henrietta Leavitt was studying variable stars in the Small Magellanic Cloud, a faint companion system near the Milky Way. While analysing photographic plates, she noticed a simple but profound relationship. Certain variable stars, later known as Cepheid variables, exhibited a tight connection between the period of their brightness variations and their intrinsic luminosity. The longer the period, the brighter the star truly was. This relationship transformed Cepheid variables into cosmic distance markers. By measuring how long a Cepheid took to brighten and fade, its true brightness could be inferred. Comparing that intrinsic brightness to how bright it appeared allowed its distance to be calculated. Crucially, this method did not depend on the star's location within the Milky Way. It could be applied anywhere Cepheids could be observed. Once this relationship was calibrated using nearby Cepheids with known distances, it became a ladder rung that extended far beyond previous limits. Distances that were once speculative could now be measured with confidence. When Cepheid variables were identified inside spiral nebulae, the implications were immediate and unmistakable. The distances derived were far too large for these objects to reside within the Milky Way. They were millions of light-years away, placing them well outside any plausible boundary of the galaxy. This was not a gradual shift. It was a step change. Overnight, the universe expanded from a single galaxy to a population of many. Objects that had been treated as internal features suddenly became independent stellar systems, each comparable in scale to the Milky Way itself. The shock was not just quantitative, it was conceptual. The Milky Way was no longer the universe. It was one example among many. A large example, certainly, but no longer central by definition. The night sky, once interpreted as a sparse arrangement of stars with a few local curiosities, became a window into a universe densely populated with galaxies. This reframing immediately altered the problem of counting. Before this recognition, the number of galaxies was effectively 1. Afterward, it was suddenly unbounded. Every spiral nebula became a candidate galaxy. Every faint smudge raised new questions. The universe did not merely contain more structure, it contained orders of magnitude more structure. Importantly, this moment did not deliver closure. It delivered disorientation. Astronomers now faced a universe far larger than expected, populated by objects that could not yet be counted systematically. Telescopes could identify some nearby galaxies, but the vast majority remained beyond reach. The question shifted from what galaxies were to how many there might be. This transition marked the birth of galaxy demographics. Once galaxies were recognized as separate worlds, it became possible to ask statistical questions. How many galaxies exist nearby? How many are large or small? How they are distributed in space? Whether the Milky Way is typical or unusual? These questions could not have been meaningfully posed before the distance scale was established. They depended on galaxies being comparable objects, rather than ambiguous nebulae. The Great Debate is sometimes remembered as a contest with a winner and a loser. That framing misses the point. The debate was resolved not by argument but by measurement. Neither position collapsed under criticism. It was overtaken by new data. The resolution also revealed a recurring pattern in astronomy. Progress often arrives not as a refinement of existing ideas, but as a redefinition of what is being discussed. Once galaxies were recognized as independent systems, the entire vocabulary of the field changed. The Milky Way became one galaxy among many. Nebulae became galaxies. The universe became structured on scales that demanded new theories and new tools. There is a subtle consequence of this shift that matters for counting. Early galaxy counts were built on a sense of astonishment. Each new galaxy discovered felt like a revelation. Catalogues grew rapidly as telescopes improved, but there was no clear sense of completeness. The sky seemed to offer endless new systems. This sense of abundance was real, but it was also uneven. Bright, nearby galaxies were catalogued first. Faint, distant ones lagged behind. The distribution of known galaxies reflected observational reach rather than true population. Still, the recognition of galaxies as separate worlds changed the baseline permanently. Counting galaxies was no longer about expanding the Milky Way. It was about mapping a population. The scale shock lingered. Even as astronomers became accustomed to thinking in terms of millions of light-years, the full implications continued to unfold. If nearby space contained dozens of galaxies, how many lay beyond? If telescopes revealed more with each improvement, was there any limit at all? These questions did not arise from speculation. They emerged directly from measurement. The universe had revealed itself to be far larger than expected, and that revelation carried a burden of uncertainty. The beginning of galaxy demographics did not provide numbers. It provided a framework, a way of thinking about galaxies as a population rather than a curiosity, a recognition that abundance, not isolation, defined the cosmos. From that point on, every improvement in observation added to the count. Not because galaxies were appearing out of nowhere, but because the means to recognize them were steadily improving. The discovery that galaxies are separate worlds did not answer how many exist. It made the question unavoidable. Once the universe was understood to contain many galaxies, counting them became a central challenge rather than a philosophical aside. And that challenge has been unfolding ever since, shaped by tools, definitions, and the quiet reminder that the universe is rarely as simple as first impressions suggest. Once galaxies were recognized as separate systems, the next impulse was straightforward. Count them. If the universe contained many galaxies rather than one, then it should be possible, at least in principle, to catalogue them, tally them, and arrive at a meaningful total. Early astronomers approached this task with the tools they had, and for the first time, those tools included the ability to record the sky systematically. Photographic plates transformed astronomy in the late 19th and early 20th centuries. Unlike the human eye, a photographic plate could collect light over long periods of time, accumulating faint signals that would otherwise be invisible. Exposures lasting hours revealed countless dim objects scattered across the sky, many of them spiral nebulae now understood to be galaxies. These plates made repetition possible. The same region of sky could be recorded, studied, compared, and catalogued. Patterns began to emerge. Certain regions appeared richer in galaxies than others. Some galaxies clustered together, while others appeared more isolated. Early catalogues were assembled from these images, listing galaxy positions, apparent brightness, and rough shapes. For the first time, the universe began to look like something that could be inventoried. But the appearance of order concealed deep limitations. Photographic plates had finite sensitivity. They responded strongly to blue light and weakly to red light. Faint galaxies with older stellar populations emitting more red light were underrepresented. Dust absorption further reduced visibility, particularly near the plane of the Milky Way. Even in the clearest regions of sky, plates captured only a fraction of what was truly there. Brightness became the primary filter, whether astronomers intended it or not. Only galaxies above a certain apparent brightness threshold made it into catalogues. Everything fainter effectively did not exist as far as the data were concerned. This is where the idea of the luminosity function enters the story. The luminosity function describes how many galaxies exist at different intrinsic brightness levels. It is not a count of individual galaxies, but a statistical description of a population. Early work on this concept recognized that bright galaxies are rare, and faint galaxies are common. The challenge lay in measuring the faint end of that distribution. Fritz Zwicky played an important role in shaping this way of thinking. While studying galaxy clusters in the 1930s, he noticed something peculiar. The motions of galaxies within clusters were far too fast to be explained by the visible mass alone. This led him to propose the existence of large amounts of unseen matter, what is now known as dark matter. Although his ideas were controversial at the time, his approach had broader implications. Zwicky treated galaxies as members of populations rather than isolated curiosities. He considered how many galaxies of different types existed within clusters, and how mass was distributed among them. This statistical mindset was essential for counting on cosmic scales. However, early attempts to apply it ran headlong into observational bias. Faint galaxies were not merely undercounted, they were often entirely absent from the data. When astronomers plotted the number of galaxies as a function of brightness using early catalogues, the curve appeared to drop off sharply at low luminosities. It looked as though there were relatively few faint galaxies. That conclusion was comforting, but wrong. The apparent scarcity of faint galaxies was not a feature of the universe, it was a feature of the instruments. Below a certain brightness, galaxies simply vanished from photographic plates. The luminosity function was being truncated by technology, not by nature. This created a systematic bias that was difficult to recognize at first. Because the same bias affected most surveys, results appeared consistent. Different catalogues agreed with one another, reinforcing confidence in their completeness. The missing galaxies were missing everywhere. Bias also crept in through selection choices. Early surveys often focused on visually interesting regions or areas known to contain clusters. Empty regions received less attention. This skewed perceptions of how galaxies were distributed across space. Classification introduced further distortion. Galaxies with clear spiral structure were easy to identify. Elliptical galaxies with smooth light profiles were sometimes mistaken for stars, especially at great distances. Small, diffuse galaxies were often ignored as plate defects or background noise. Even when faint galaxies were detected, their distances were hard to estimate. Without reliable distance measurements, it was difficult to determine whether a faint object was a small nearby galaxy or a large distant one. Many were excluded from counts simply because they could not be placed confidently. All of these factors pushed early galaxy counts downward. The universe appeared simpler and less crowded than it really was. Estimates of the total number of galaxies rose slowly as surveys expanded, but they remained anchored to bright, easily detected systems. The true abundance of faint galaxies remained hidden. There was also an implicit assumption at work. Early astronomers often assumed that the galaxies they could see were representative of those they could not. This assumption seemed reasonable. It allowed small samples to be extrapolated to large volumes, but it relied on the idea that galaxy populations did not change dramatically with brightness or mass. As later observations would reveal, that assumption does not hold. The majority of galaxies are small and faint. Their contribution to the total number is overwhelming, even though their contribution to total light is modest. Early surveys captured the light budget of the universe reasonably well, but they missed much of the population count. This distinction between light and number is subtle but crucial. A small number of large galaxies can dominate the light in a given region of space, while a vast number of small galaxies dominate the count. Counting light is easier than counting objects. Early astronomy, constrained by technology, effectively counted light. The methods themselves embedded this bias. Detection thresholds were fixed by plate sensitivity. Classification schemes favoured well-resolved shapes. Survey areas were chosen for convenience or interest rather than statistical completeness. Each choice seemed practical. Together they shaped the picture of the universe. These early efforts were not failures, they were necessary first steps. They established that galaxies existed in large numbers and that they were not distributed randomly. They introduced the statistical tools that would later be refined and corrected. Most importantly, they revealed that counting galaxies was not a simple act of observation. It was an inference problem. As technology improved, astronomers began to revisit these early catalogues, comparing them with deeper observations. Discrepancies emerged. Regions once thought to be sparse were found to contain many faint galaxies. Clusters appeared richer when observed with more sensitive instruments. Corrections were applied. Luminosity functions were extended toward lower brightness. Biases were quantified and modelled. Each correction pushed galaxy counts upward. The early attempts to count the universe did not produce a final number. They produced a lesson. The number of galaxies one finds depends on how one looks, what one is able to detect, and which assumptions are built into the method. That lesson would guide every later effort, as astronomers move from photographic plates to digital detectors, from hand-drawn catalogues to automated surveys, and from counting what is obvious to accounting for what is almost invisible. The universe had already been crowded. It was only beginning to be counted. Distance in the universe is never just distance. Every time light travels across space, it also travels across time. This means that looking farther away is the same as looking further into the past. Nearby galaxies are seen as they exist now, shaped by billions of years of evolution. Distant galaxies are seen as they were long ago, often when the universe itself was much younger. This effect is known as look-back time, and it changes the meaning of observation in a fundamental way. When astronomers observe a galaxy 10 million light-years away, they see it as it was 10 million years ago. At 1 billion light-years, the image captures a state from 1 billion years in the past. At even greater distances, galaxies are seen during their earlier stages of formation. As a result, the universe does not present a single, uniform population of galaxies at different distances. It presents a layered history. Nearby galaxies tend to be mature systems. Many have settled into stable structures, with star formation occurring at moderate rates or having largely slowed. Spiral arms are well defined. Elliptical galaxies contain older stellar populations. These galaxies reflect the outcome of long evolutionary processes, including mergers, interactions, and gradual gas depletion. Distant galaxies tell a different story. They are often smaller, more compact, and more irregular. Star formation rates tend to be higher. Structures are less settled. Some appear clumpy or distorted, not because they are abnormal, but because they are young. This intrinsic difference matters deeply for counting galaxies. If distant galaxies were simply farther away versions of nearby ones, counting would be relatively straightforward. One could correct for distance and brightness, then extrapolate. But because galaxies evolve, the distant population is not a mirror of the nearby population. It represents earlier stages in the life cycle of galaxies. This complicates any attempt to estimate how many galaxies exist at a given time. The challenge is compounded by the concept of an observational horizon. In relativistic cosmology, the observational horizon defines the maximum region of the universe from which light has had time to reach an observer since the beginning of cosmic expansion. Beyond that boundary, light has not yet arrived, regardless of how powerful a telescope might be. George Ellis has written extensively about these horizons, emphasizing that they are not physical edges or walls, but limits imposed by time and the finite speed of light. The observable universe is not the entire universe. It is the portion that has had time to reveal itself. This distinction is essential for galaxy counting. Any count is automatically restricted to the observable universe. Galaxies beyond the horizon may exist in enormous numbers, but they cannot be observed directly. They must be excluded from empirical counts, even if theory suggests their presence. Within the observable universe, distance still introduces additional limits. As galaxies recede farther into the past, their light becomes fainter and more stretched. This stretching affects not only the colour of light, but also how it is distributed across the sky. One of the most important consequences is surface brightness dimming. Surface brightness refers to how much light is received per unit area on the sky. As distance increases, the total light from a galaxy spreads over a larger area, and the expansion of the universe further reduces the energy of that light. The combined effect causes surface brightness to decrease rapidly with distance. This means that even if a distant galaxy has the same intrinsic brightness as a nearby one, it will appear much fainter per unit area. Extended, diffuse galaxies suffer most from this effect. Their light becomes so spread out that it falls below detection thresholds, even when their total luminosity might be substantial. Compact galaxies fare better. Dense regions of star formation can remain visible at great distances, while extended disks fade into invisibility. This introduces a selection effect that favours certain types of galaxies over others as distance increases,